Okay, so welcome to section 4.5, which is logarithmic properties. Logarithmic properties. Okay, so let's recall some properties of exponents. So recall, if I have a to the m times a to the n, I can combine the exponents as a to the m plus n. Similarly, if I have a to the m divided by a to the n, this can be written as a to the m minus n. That is top exponent minus bottom exponent. And if I have a to the m raised to the n, that's going to be a to the m times n. So these are some properties of exponents I want us to recall. Maybe I'll do quick examples. So for example, if we have 3 squared times 3 to the 5th, that's going to be 3 to the 2 plus 5, or 3 to the 7th. In the second case, let's say we have 2 to the 4th divided by 2 cubed. It's going to be 2 to the 4 minus 3, which is 2 to the 1st. In the third case, let's say we have 5 squared cubed. That's going to be 5 to the 2 times 3, or 5 to the 6th. So that's what these properties represent. So let's consider, I probably shouldn't have used that orange. Shoot. Okay, well, sorry. Let's consider the following. Let's let, m be equal to log base a of m. Yes, one of your classmates said because I don't have much homework. I don't do much work. That was funny. Anyways, n is equal to log base a of n. Okay, so let's define m and n as logarithms, both base a, little m with an argument of capital M, and little n with an argument of capital N. Okay, and then let's let y be equal to log base a of m times n, both inside the argument of the logarithm. So let's translate this to exponential form. That is, let's evaluate base raised to the answer is equal to the argument. So, oops, oh my goodness, I guess I forgot to change that. Let's have, nope, it's not going to do that. There we go. So a raised to the y. And then that's going to be set equal to the argument of what's inside. Okay, so we'll have a raised to the y is equal to m times n. Okay. Pardon me. But let's actually, I forgot, I should probably be explicit up here. Okay, if I have m is equal to log base a of capital M, do we agree this is equivalent to saying base A raised to the answer m, little m, is equal to capital M? Come on. Over here, if I have little n is equal to log base A of capital N, then base little a raised to the answer little n is equal to the argument capital N. In both of these cases, I've just done the circle. Base raised to the answer is equal to the argument. Base raised to the answer is equal to the argument. That's a definition of logarithm. So I didn't explicitly show that, now I'm doing that. The reason I'm doing that is because then I can rewrite capital M as little a to the m as defined above. And I can rewrite capital N as little a to the little n as defined above. Okay. But now I can use properties of exponents to rewrite the right-hand side as a raised to the m plus n using the properties of exponents above. Okay. Well, what that means then is that y must be equal to m plus n, because the base is the same on both sides, so the exponents must be equal, right? Okay, so we have y is equal to m plus n. Well, that means that y is equal to, what was little m? It was log base a of capital M, to which we're adding what was little n? It was log base a of capital N. Okay, so that's what we have for y, but what was y? It was log base a of m times n. So therefore, I get that log base a of the product m, go back, of the product m times n is going to be log base a of m plus log base a of n, and this is known as the product rule. I'll write that, here. This is the product rule. Don't worry, we will formally define these in a moment. But I may as well put a box around it because it's that important. And we'll write a theorem with it. Oh, wow. Oh, my goodness. What is going on? What in the heck? Okay, no, that's not what I wanted. Yeah, it's been crazy. I can't even draw a box. Okay, there we go. Okay, so we're okay with that. Well, let's see another consider, only this time with a bit darker orange. So let's consider so we still have m and n as defined before. So I'll just copy and paste these. They're the same ones I want to use. Okay. Okay, so now let's let y be equal to log base a. Now let's do a quotient. Let's do m over n. Okay, so that means, this implies that base raised to the answer is equal to the argument. So this implies that a raised to the y is equal to the quotient m over n, if I do my little circle. So hopefully you see that. But maybe I should show it explicitly, so let me move this down so you see where I'm getting that from. So I'm doing base raised to the answer is equal to the argument. Okay. Okay, so what do we have? We know that a to the y can really be written as, what is capital M? Well, we've defined capital M to be base A raised to the little m, and we've defined capital N to be base A raised to the little n. Okay, so what do we get here? We can use the quotient rule for exponents, and this will be A raised to the m exponent in the top minus n, the exponent in the bottom, by definition, right? Okay, well, since the bases are both the same on either side, this must mean that y is equal to m minus n, because the exponents are the same. Okay, so let's bring this over here. So we have that y is equal to m minus n, little m minus little n, but little m was log base A of capital M, whereas little n was log base A of capital N. Okay, and since y was log of base A of m over n, we can now write, therefore, maybe I should move this up one line. There, okay. So therefore we have, pardon me, we have log base A of the quotient m over n is equivalent to the difference of log base A of m minus log base A of n. And this is known as the quotient rule. And like I said, we will repeat this in a moment. So note it in your brain right now. We'll formally write it down in a second. So this is a quotient rule. No, it's not going to autocorrect. Okay. Oh my goodness. Really, drawing a square shouldn't be that. Rather a box. Okay, there we go. Okay. One more. So we've done the product rule, the quotient rule. So now let's consider a third rule. And I'll do this consider in should I do it in red? No, I'm going to do it back in regular orange. So let's consider. Once again, I'd like to define, no. For this one, I'm only going to define one. Let's let, pardon me. Oh my goodness. Okay, so let little m be equal to log base A of capital M, which we know is equivalent to saying base A raised to the answer little m is equal to capital M. Okay, so now we're going to let y be equal to log base A of m to the r. So this is equivalent. Actually, let me write that M in blue so it's explicit. And maybe I'll write the R in a different color so that's explicit. Let's do green. Okay, so this implies that base A raised to the answer y is equal to the argument m raised to the r. Okay, so this is base raised to the answer is equal to the argument. Okay, so we have that a to the y is equal to, well, what is m? M is a to the little m, and that's what I'm raising to the r. Okay, so when we raise a power to a power, we multiply. So this is a, base a, raised to the m times r. But much like 3 times 15, 3 times 5 is 15, 5 times 3 is also 15, so the order doesn't matter. And for this problem, let's just go ahead and put r times m. You'll see why I'm doing this in a moment. Because now, if the bases are the same, I can equate the exponents. It must be the case that y is equal to, r times m. Okay, but what was little m? Well, little m was log base a of capital M, right? So little m is log base a of capital M. Okay, so therefore, since y is equal to y, we know that this y up here must be this y down here. So we have that log base a of m raised to the r is equivalent to r times log base a of m. And this is known as the power rule. Power rule, because it deals with an exponent or power. So each of these were proofs, so they may come up again in some sort of an assessment. Okay, so let's write these as a theorem. So theorem, and this is rules or properties of logarithms. So properties of logarithms. Okay, so property number 1 is the product rule. Log base a of m times n is log base a of m plus log base a of n. Okay, so this is the product rule. When you multiply things together, we add. Now let's do number 2. Let's do log base a. Do you know what? I'm going to move. I guess I'll be okay. Of m divided by n. So this will be log base a of m minus log base a of n. And this is the quotient rule. So when we divide, we subtract. So quotient rule or division yields the subtraction or difference between two logarithms. And number 3, when I exponentiate, so log base a of m raised to the r is going to be r times log base a of m. So this, of course, is the power rule we just stated. So we've proven why each of these is indeed a property of logarithms. So let's apply them now. So for example, so let's express the following as a single logarithm. So express the following. Express the following as a single logarithm. So number one, let's say we have 2 times log base 3 of x plus 4 times log base 3 of x minus 5 minus log base 3 of x squared. Okay, so there's a few things going on here. So I'm going to color code. This is 2. And let's just do log base 3 of x plus 4 times log base 3 of the quantity x minus 5, then minus log base 3 of x squared. Okay, so the first thing I'd like to do is put each of these coefficients into the exponent. So what I'm going to get then is going to be a log base 3 of x squared plus log base 3 of the quantity x minus 5 raised to the 4th, and then minus log base 3 of x squared. Okay, so now let's do the product rule for these two guys. So here, I'm going to use the product rule because there's a sum in between those two. So there's a sum here. So we use the product rule. So this can now be written as log. Notice they're both base 3. And this is going to be x squared times the quantity x minus 5 to the 4th power, from which we're subtracting log base 3 of x squared. So now we have a difference, right? So now that we have the difference between two terms, two logarithmic terms, with the same base, this will now be the quotient rule. Meaning, this is going to be log base 3 of, in the numerator, we will have the x squared and the quantity x minus 5 to the 4th. But now in the denominator, we will have x squared. Interesting. Because what's going to happen now, looks like I have the same factor in the numerator as I do in the denominator of the argument. So this actually simplifies, and let me rewrite this log as log instead of something that looks really weird. Log base 3. Okay, so do you agree that this simplifies to log base 3 of the quantity x minus 5 to the 4th? And there we are. Okay, so that is a single logarithm. Now let's do number 2. Oops, oh my goodness. Okay, so number 2. Let's say we have natural log of e cubed minus natural log of 1 plus 1/2 times natural log of e to the 8th. Okay, so I'm going to write this as natural log of e cubed minus natural log of 1. I'm just going to leave that the way it is. Plus 1/2, pardon me, natural log of e to the 8th. Okay. Well, the first thing I note is that any base, log base a of 1, is 0. So I can just rewrite this as natural log of e cubed plus, and let me go ahead and move this into the exponent. So this is going to be plus natural log of the quantity e to the 8th, then raised to the 1/2 power. And when we raise a power to a power, we multiply. So this is natural log of e cubed plus natural log of e to the, well, what's half of 8? Half of 8 is 4. So now we can finally use which rule if it's a plus? That's a product rule. So product rule. Meaning I can rewrite this logarithm as natural log of e cubed times e to the 4th. Okay. So do you agree that that's natural log of e to the 3 plus 4? 3 plus 4. Okay, so that's natural log of e to the 7th, right? Okay, but what was the base of natural log again? It was defined to be log base what? E of e to the 7th. Okay, interesting. So I'm looking for the power to which I must raise e in order to get e to the 7th. Or, even better, let's use our properties of power properties, or power rule. Bring the 7 down in front. This is log base e of e, which, what power do I need to raise e to in order to get e? That's just 1. So this is just going to be 7 when all is said and done. Okay. Look at that. That simplified just to 7. Okay, and this is because log, actually, e, no, I'll write it, sorry, log base e of e equal to 1 is the same thing as saying e to the 1st is e, which it is, right? Base raised to the answer is equal to the argument. So this term here just goes to 1. Okay, so let's do 3. Third time's a charm, so 1, 2, 3. Let's say we have, let's do 3 log x plus 1 plus 2 log of x. Okay, so only 2 guys here. So rewriting, let's do 2 times log of the quantity x plus 1 plus 2 times log of the quantity x. Okay, so the first thing I want to do is deal with the exponents. So I want to put each of these in the exponent. So what I get first is I have log of the quantity x plus 1 squared, to which I'm adding log of x squared. And now that I see these both have the same base, what's the base here? If it's not explicitly written, it's common logarithm, so it's base 10, right? But we're going to use the product rule here. Product rule. Okay, so that means I just take the product of the two arguments. So we have log, common log, of the product quantity x plus 1 squared times simply x squared, and there we are. That's sufficient. That is a single logarithm. Okay, so now let's go the opposite way. So let's, for example, let's expand now. So expand the following logarithms. Expand the following logarithms. Using properties of logarithms. Okay, so number 1. Let's say we have natural log of the quantity x cubed times the square root of x times the fifth root of x plus 1. No, let's do x minus 1. Doesn't really matter. Okay, so we have natural log of the quantity x cubed times the square root of x times the fifth root of the quantity x minus 1. Okay, I have a product 1, 2. I have 3 factors in this product. So I'm going to use the product rule because this is a product. So product rule. And the product rule states I can expand to addition. So this will be, what's the base here? E, it's natural log. So this will be natural log of the first term of the product, to which I will add natural log of the second term, or the second factor rather, of the product, to which I will add natural log of the third factor in this product, namely the fifth root of the quantity x minus 1. Okay, so that's the product rule in action there. Okay, so now it's supposed to autocorrect to an arrow. Nope, is it not going to do it? Oh, well, that's a terrible arrow. Okay, well, never mind. I'll just do it this way. Okay. So now I'm going to use the power rule, at least for the first term. So I'm going to take the exponent 3 down in front. So this will be 3 times natural log of x. But I can use the fact that roots can be written as fractional exponents. So the square root is natural log of x to the 1/2, whereas the fifth root is going to be a fractional exponent of 1/5. Okay, so my next step is to use the properties, the power rule, to bring the 1/2 and the 1/5 out in front for the second 2 of the 3 terms. So we will have 3 times natural log of x plus 1/2 times natural log of x. Interesting. Those are like terms, aren't they? It's like I could add them. And then this will be plus 1/5. Oops, 1/5, not 1/3. 1/5 natural log of the quantity x minus 1. Now notice I can combine these two because they both are natural log of x's. So since their arguments are equivalent, do you agree that 3 is equivalent to 6/2? So adding 1 would be 7/2. So this is 7/2 natural log of x, to which I'm adding 1/5 natural log of the quantity x minus 1. Okay, so that's as expanded as possible, while also adhering to the rules of math. Okay, so I don't know if I needed that much of a space in between. Well, let's do number 2. Let's say we had log of the quotient. So in the numerator we have x plus 4 to the 5th. In the denominator we have x squared. And the quantity x plus 1 cubed. Okay, so we have log of the quotient. Oops, okay. Let's do, in the numerator, let's go ahead and have x plus 4 to the 5th power. Then in the denominator, we'll have x to the second power. Then we'll have quantity x plus 1 cubed. Okay, so the first thing that's most evident is the quotient. So I'm going to use the quotient rule, right? Actually, let me just, this is a quotient. So we're using the quotient rule, meaning top minus bottom. So I will have log of the numerator, namely quantity x plus 4 to the 5th power, from which I'm subtracting log of the denominator, which is the product x squared times the quantity x plus 1 cubed. Okay, so actually let me move this over so I have more room. Okay. Well, I can use the power rule to bring the 5 down in front. Log of x plus 4. Then minus, I can actually use a product rule because this is a product here. So this, I can write this minus the quantity log of x squared plus log of the quantity x plus 1 cubed. My goodness, what is wrong with me? Okay, so I can, let's go ahead and distribute the negative inside that bracketed remark. So we'll have 5 log of the quantity x plus 4 minus log of x squared, and then once again minus log of the quantity x plus 1 cubed. Now notice anything that was in the denominator has a minus preceding it. Okay, going to the next page. I can now use the properties, the power rule, to bring the power down in front. So this is 5 times log of the quantity x plus 4 minus, this will now be 2 times log of x, and minus, so now be 3 times log of the quantity x plus 1. Okay, so that is expanded as possible, and there are no like terms. I wonder if I could have given myself an extra space. I don't know if I can. Sorry that I went to the next page. Okay, so number 3. Actually, let me move this down. It's going to be a big quotient. So let's say we have log base 3. Now in the numerator, let's say we have x squared, y cubed, and z to the 4th. But in the denominator, let's have x plus 1 to the 5th. Okay, so we have log base 3 of the quotient x squared, y cubed, z to the 5th, divided by the quantity x plus 1 to the 5th. Oh, that's z to the 4th, sorry. Oh, counting, not my strong suit. Okay, so clearly this is a quotient, so the first thing I'm going to use is the quotient rule, meaning subtraction. Okay, so this can be expanded as log base 3 of the numerator, which is quantity x squared, times y cubed, times z to the 4th, from which I'm subtracting log base 3. Really, are they biting me, these ants? Log base 3 of the denominator argument, which is x plus 1 to the 5th. Okay, now it should be clear I can break up the first logarithm into the sum of 3 distinct logarithms because I have a product with 3 factors. So this is log base 3 of the first factor, x squared, plus log base 3 of the second factor, y cubed, plus log base 3 of the third factor, z to the 4th, from which, pardon me, I'm subtracting. Now I can use the power rule for this last factor. So 5 times log base 3 of the quantity x plus 1. Okay. So now let's use the power rule for each one here. So we will now have 2 times log base 3 of x. Then we will have plus 3 times log base 3 of y. Then we will have plus 4 times log base 3 of z. Then we have minus 5 times log base 3 of the quantity x plus 1. Okay, so that's the expansion. Okay, holy free holy. Where are we? Okay, so let's do a darker orange here. So let's consider the following. Let's do y is equal to log base a of m then this implies, of course, that a to the y is the same as m. So I'm going to focus on this second equation here. This implies that if I evaluate log of both sides, let's do log base b of a to the y. That's going to be equal to log base b of m. I'm just evaluating log of both sides, right? Okay. So far so good. Well, do you know, I can bring out the exponent on the left. So why don't I write this as y times log base b of a. And that'll be equal to log base b of m. Okay, so how would I isolate y? Well, in order to isolate y, I would need to divide off what's attached to it, which is log base b of a. So if I divide both sides, I'll have log base b of m divided by log base b of little a. And what was y? Was log base a of m. So what can I state therefore? I can state that the y began with, namely, log base a of m is equivalent to the quotient log base b of m divided by log base b of the previous base a. So this is known as the change of base formula, because I've changed from an expression with base a to an expression with base b. Okay, so change of base formula. Change of base. And it is simply that log base a of m is going to be the quotient log base b, some other base, of the argument over log base b of the previous base. So notice the way I remember this is m is over a and m is over a in both cases. So that does help. Okay, so for example, so express the following. With respect to base e. Okay, so number one, let's say we have log base 9 of 22. Okay, so log base 9 of 22. I want to express this with respect to base e. Well, what's base e? Base e in a logarithm is natural log. So I claim this will be natural log in the top and natural log in the bottom. And since m is still over a, we have that it'll be natural log of the argument 22 divided by natural log of the previous base 9. And there we are. Okay, so number 2, let's have log base 6 of 12. So let me use a different color here. What color should I use? think I'll use pink. So we have that log base 6 of 12 is going to be the quotient that uses as its base e, meaning natural log, ln. I have that the argument is in the numerator, and the previous base will be in the denominator. And there we are. Okay. So before I end, I'd like to consider some properties of log. So let's consider, pardon me, I claim that log base a of 1 is equals to 0. Well, is it true that base a raised to the 0 is 1 for all positive bases? Well, actually, even for 1, but logarithms are defined as not having a base of 1. But you get the idea that this is true. Okay. What about, let's have log base a of a. I claim that that's equal to 1. Well, is it? Is base a raised to the first power equals to a? Yes, it is. Check mark. Okay. That's good to know. What else? Number 3. Let's say I have log base a of a to the n. I claim that that's n. Oops, what's going on? Well, is that true? Is base a raised to the n equals to argument a to the n? Yes, it is. Okay, so these are a couple of properties that I was using, and hopefully you understand now why they are what they are. And here I will end this section here and see you in the next section.